So yeah, I will talk about the evolution of functionality in agent-based system and how they're able to see or to perceive their environment, and how the structures can be logically analyzed. First, few introductory remarks. Without any ambition to go into discussion of what are the overall properties of living systems that should define them as they are and as they could be. In this work, we focused on one of their aspects, which is their ability to develop any sort of adaptive reactions to environmental inputs, especially to novelty they can observe. And this property of living systems can be observed both at evolutionary scale and also during the development of a single organism. Of course, in evolutionary higher organisms, we have a clear evidence of learning, where we, for example, we as humans can quickly adapt our set of actions to some newly perceived environmental impact, but also at the level of single cells, we can see the similar, albeit much less complex, ability to adapt to external changes. For example, development of drug resistance in tumor cells is driven by the ability of tumor cells to adjust the expression of, let's say, efflux pump proteins as a response to perceived increase in local concentration of drugs. At the same time, at the evolutionary scale, we can see the similar phenomenon, which is quite obvious if we look at any living system now, because any living system now is here exactly because it was during the evolution able to find his or her own ecological niche, and over time and over generations became adapted to that niche. Of course, it opens a question of mutual interaction between ecological niche and in a sort, in a kind of way, the organism, by selectively perceiving a subset of environmental properties, is able to construct personal or subjective idea of environment, and at the same time environment during evolution shape that organism. So we have over time some sort of mutually strong connection. But behind all of these questions, we tried to analyze how exactly an agent or an organism is able to deal with such novelties it will inevitably perceive in environment. And we focused on two aspects. The first one is their ability to incorporate these environmental parameters into existing functional traits and just to optimize what he already knows. And the other mechanism would be to actually create entirely novel functional combinations. And behind both of these points is an implicit assumption about existence of a sort of functional atoms, and I will return to that a bit later when talking about embodiment. So we tried to focus our work on a problem, as I just said, and we tried to define it as a problem of building of subjective frame of reference. By frame of reference, we mean ability of organism to functionally distinguish environmental properties. And by functionally, we mean association of a certain environmental property with a set of actions that should be performed as a response to that property. And if we look at things in that way, we think that there are two main building blocks in developing frame of reference. And these building blocks are ability to segregate and ability to categorize environment. By segregation, we mean possibility or ability of agents to distinguish environmental objects. In other words, to perceive something in the environment as a distinctive object. The other categorization is ability to develop a variety of functional responses to performed segregation. In other words, if I see, let's say, a pen, I'm able to segregate it into a single object, and I already know, because I learned over my life, what could I do with that pen? I could take it, write it with, throw it someone, or similar things. So that's why it is categorization. And of course, real-world environment is extremely complex, and that's why quite unpredictable and with a high probability of novel and unexpected things happening. So the question is, if we have those elements, segregation and categorization, to what extent they are stable, and also how exactly such adaptability can be achieved. Because if they are too stable, the fast enough and will probably go extinct. But on the other hand, if they are too flexible, we will not have any kind of stable behavior, and the fate will probably be again extinction. So during learning or evolution, organisms need to find a balance between these two extremes, stability and fluidity. So in this work, we investigated the emergence of a single frame of reference for a given static input, which is actually word state in our agent-based system. We started with the static input, but then we experimented also with the ability of our agents to follow movable inputs, and I will show you some preliminary results on that. Again, our question we struggled with is what should be the minimum predefined structure we should impose on such system? Because, well, this kind of minimum structure, at least for me, would be a holy grail of the entire process of building such agents. And at this stage, we of course didn't succeed in that, because I guess that the minimal necessary imposed structure would be just to put building blocks and then expect that somehow the overall architecture emerge. But at this stage of work, we realized we need first to define some set of embodied actions. And we need to draw at least a sketch of a global architecture. In future works, we will try to make this sketch even more fuzzier and to see what is happening. But for now, we have a set of embodied actions, and they are quite basic. Our agent can focus, which means that he can pick up a single pixel in the environment where he resides, and that's it. The focus is just picking up a single pixel. Move focus is just randomly moving focus, as it says. Then he's able to interact with this pixel. And in our simple setting, interaction means either some sort of positive gain or negative gain, because it was the most simple way to implement such system. So interaction could result in either some abstract positive gain or something negative. Also, he should be able, because it is all organisms, when they have receptors for anything, these receptors are based on underlying physical and chemical properties. So in real systems, receiving any kind of input from the environment automatically means analyzing that. So if we have, for example, a receptor for, I don't know, some kind of sugar in cell wall, a specific receptor will be activated, and the goal of evolution is to connect this receptor with the rest of internal actions to gain something useful out of it. So in our setting, we again go for a sorry. Oh, okay.
The last thing I wanted to speak about today is VCAT. So VCAT is clearly where we go if tenants haven't been paying their rent or for bond and compensation claims and those sorts of things. There is a massive, massive backlog. They're talking about 7,000 cases in the backlog in VCAT at the moment. During this period, they've moved to telephone conferences and what they call papers conferences, where we submit everything into VCAT. What they've found is both of these conferences are actually slower than having them face-to-face. And they are, from what I hear, suffering a real critical shortage in terms of VCAT members.
Okay, it seems
so
that something is messed up with audio.
That they're going to hear. They've really spoken about the fact that urgent repairs are number one. Danger.
Yeah. Now, is it now fine? I guess now it's fine.
I hope so. Yeah.
Yeah. It seems someone turned on their mic. Okay, I will continue. So in our setting, the world is just a set of pixels, and each pixel can be or black or white or 0 or 1. So analyzing this simple world means just picking up whether the agent would like would recognize whether this color of the single pixel is black or white. And at the end action, which should signalize that the sequence of actions should be stopped. And the overall architecture is here in a simplified way. So in the upper left corner, we have the white, some of them are gray or black. and the agent should observe. The agent is a completely blank slate, so he and these architectures, this architecture, but he does not know exactly what he should do with anything. And at each time step, he can random sequence of these embodied actions, execute them, and see what happens. We designed the simulation that we recognize and analyze black squares, he will get a reward, and for white squares, he will get nothing. So his incentive over time should be to learn to recognize black squares and to focus on them. So just to quickly go over it. At each step, since he have only a set of actions, he can, for example, choose to focus, and, or focus, move focus, and. And a similar set of completely meaningless actions. Of course, our hope is that over time he will be able to discover something meaningful, like focus, analyze, interact, and which would be a minimal, most effective way to get a reward. And we run simulation such that at each time step he can, in his subconsciousness, create several candidate sequences, pick up one of them, execute them, memorize the overall effect of such action, and build up this memorized effect into an overall network of interacting embodied actions for a given pixel. So over time, we will get hopefully a full network, but links are weighted and directed. So over time, he will just start to learn to execute optimized, most optimized sequence of actions for any given pixel. And let me try to show you how it looks. Okay, so this is the subjective experience of our agent. We have a gray square. Gray means that he did not visit those pixels. When he visits any pixel, he built up a score of that pixel, and over time you can see that just by chance he will visit all pixels, and at the middle of his vision is hidden black square, and over time we can see that he is actually focusing on this area and starting to optimize how he look at it. You can see blinking colors because at each time step he have probability of extracting from the overall network what would be the optimal path, and also possibility of exploring further modification to that path. But over time, as you can see, the square he is recognizing is becoming darker and darker, which means
we lost your voice. Okay.
Okay. After that, we tried to see how he will be able to adapt to a changing square. So in this simulation, we put a single square at the middle of the world, then moved that square at the bottom left, at the top left part, and then moved it at the bottom right part. And you will see that the beginning is quite the same. He started learning that there is something interesting at the and over time, I guess soon we will move the square. Just check. Yeah, now the square is moved. He started losing interest in the central area, but he started focusing at the top left area. So we actually wanted to show that the entire architecture is able to quite flexibly relearn everything which encounters. And now we moved the black square at the bottom right angle. And then, as you can see, he started moving his attention to that area. Of course, the entire system is unoptimized and quite slow, but at this stage, our
Igor,
goal was
your
just to
sharing might be paused.
So, yeah.
Sorry to interrupt. Your screen sharing might be paused because we don't see the changes.
I see. And what do you see now? Maybe I could stop sharing and then returning just to check. How should I stop share? Stop share. Okay, and now I will try again. So here is the experiment with moving object. As you can see, he is starting focusing attention on the central square. Soon we will move the black square at the top left corner, and you will see that.
Actually, I don't see anything. I see on the phone.
Sorry for that. I just don't.
Yeah, maybe you need to share your desktop because you switch to another application and we see the previous.
I see. Okay. Stop share. I see. Maybe. Okay, I guess those agents are much smarter than I am with these technologies. So let me try it now. Share screen. Yeah, do you see it now?
I think yes, but I'm not sure what we have to see. But yeah, something is happening.
Okay, so should I continue? Can you see it or no?
No, we can see that something is happening.
Okay, I will move forward. Okay. So previously, the agent focused on the center part. Now we moved target to the upper left corner, and you can see that he's focusing his attention to that area, and now we moved it bottom right part, and the attention again slowly switched there. So what is happening behind the entire structure? Okay, let me check this. Yeah, okay. So here we have how those networks look like. And as you can see, over time, he started building connections between those embodied actions. Each action is a single node, and the size of a node reflect the sum of incoming weights of links between nodes. And this is a sample of underlying architecture of recognizing a black pixel. And as you can see, okay, here's a bit faster. He is focused on, we called it internally metabolized, which is actually interaction. He is focused on moving focus, analyzing color, and interacting with a single agent. But in contrast with that sample architecture that was built in response to an empty pixel is like this. They were connected, but links have a negative or very small weight, and they're quite static, and nothing especially interesting happens there. So okay, let me try to wrap up things. Share. So what? Yeah, my time is up. Okay, I will skip several slides. So what are the next steps? Oh, sorry for that. What we are trying to do now is actually, at one hand, to optimize the entire procedure, to go even faster towards convergence of putting focus at some place and analyzing it. But what we find even more interesting is development of a sort of metastructures, because right now for each pixel we have a small, very focused network of interactions between embodied actions. But it will be quite interesting to see how those local perceptive interactions will merge into a larger structure that could guide more intelligent behavior. After we do that, we will of course go with increasing complexity of our world with more properties imposed on pixel, and more varieties with the changes. So that's my talk. Sorry for the technical problems, but I hope it was manageable. And okay, now I should stop sharing. Yeah, no, it's fine.
Yeah. Well, thank you very much for impressive talk. So do you have any question or comments? So may I have one quick question? Your system is aim of your system. You creating this model to understand the emergence structure, or you would like to apply some real world things.
Mm-hmm.
Yeah, which is your main topic, main aim of your study?
I see. Yeah. Well, the underlying assumption is that when we perceive our environment, we are not exactly optimized to perceive it as it is, but more to perceive it as it is most useful for us to survive. So the aim is so basically we all live in a sort of illusionary world, which is useful for us, but we cannot claim that it is a true world. So one of the aims here is to investigate exactly that discrepancy between objective world, we can control it, and how subjective perception emerge in such situation, and to what extent such a subjective illusion will converge towards objective reality in different settings. Because this one is quite simple setting, but it would be, I guess, interesting to include more complexity in the world where agent can be killed, or will need to develop a more fine-grained resolution of interacting with the environment. So yeah, these are the main topics we are dealing with.